Let's start illustration number 13, in which we have to prove that for free LC oscillations, the sum of energy stored in the capacitor and the energy stored in the inductor is having the constant value at any time. So first of all, I start my analysis at time t is equal to 0. The charge on the capacitor is equal to Q0. That means this is the initial capacitance, and when this capacitor is connected with the inductor parallelly, then free oscillation starts, and these free oscillations are having the angular frequency 1 over under root of LC, and therefore after charging the capacitor, the instantaneous charge is given by Q is equal to Q0 cos omega 0 t, and the electric current I is the rate of change of charge with respect to time. So this is basically the differentiation of this cosine function, and we know the differentiation of cosine function is minus sine, and the Q0 will be as it is, and the differentiation of inner part is omega 0. So the value of I is obtained, and it is periodically changing with time, but we have to show that the value of energy is constant. So in order to find out the energy, that is stored in the capacitor is given by which kind of energy? That is potential energy, and the potential energy UE is equal to 1 by 2 CV square, and the value of V, which is related to the total charge Q by the relation Q by C. So here I am substituting the relation C into Q square over V square. Not V square, here this square will come, and the C in the numerator and the denominator will be cancelled. So the actual potential energy or the energy stored in the capacitor is Q square upon 2C. Now the value of Q is given by Q0 square over 2C into cos square omega 0 t. Therefore, UE is equal to Q square upon 2C cos square omega 0 t. Now at the same time, the energy stored in inductor we also have to find out. Therefore, the energy stored in the inductor is given by UM is equal to 1 by 2 Li square, which is equal to 1 by 2 L. The value of I we have earlier obtained. So minus square is plus Q0 square omega 0 square sine square omega 0 t. So this is the value of the energy stored in the inductor. But we know the value of omega 0, that is 1 over under root LC, and its square is 1 over LC. So 1 by 2L Q0 square. Instead of omega 0 square, I am writing 1 over LC into sine square omega 0 t. So L is cancelled out. Now the final equation for energy stored in the inductor is given by Q0 square upon 2C sine square omega 0 t. And now the total energy we have to find out. And I am denoting the total energy as U is equal to UE plus UM. Now see, that is particular meaning why we have used the subscript E and M. Because when we consider the energy stored in the capacitor, we are considering the electric field. And whenever we start our analysis to find out the energy stored in the inductor, then we are dealing with magnetic field. And for magnetic field, I have used here the subscript M. And now, from the values of UE and UM, this value Q0 square upon 2C is coming common. And inside the bracket, cos square omega 0 t plus sine square omega 0 t. Now, cos square theta plus sine square theta is equal to 1. But instead of theta, here we have omega 0 into t. But it doesn't matter. The relation means cos square plus sine square will be 1. And therefore, the total energy is equal to Q0 square upon 2C. And here, if you see that the charge and capacitance C are independent of time. Why? Because at time t is equal to 0, the inductor is not connected, and hence there will be no change in the value of charge. And hence this total quantity U is equal to constant. So we have proved that the total energy stored in the capacitor and inductor is constant. Illustration number 14. In an LCR AC circuit, the value of inductor is provided. L is equal to 5 Henry, and the value of angular frequency, that is omega, is given by 100 radian per second. And it is actually the angular velocity, remember. And the value of resistance is given by 100 ohm. And the power factor, what is the value of power factor? Means cos delta, that is 0.5. And now, according to the formula of power factor, it is given by cos delta, which is equal to R over modulus of Z or magnitude of Z, and the magnitude of impedance is given like this, under root of R square plus omega L minus 1 over omega C whole square, and that is equal to cos square delta is equal to R square divided by R square plus omega L minus 1 over omega C whole square. Therefore, the value of cos delta is 0.5. So if I do it square, then it will be 0.25. And I can also write 0.25 as 1 by 4, which is equal to r square divided by r square plus omega L minus 1 over omega c whole square. Now cross multiplication, therefore 4r square in the left hand side I am writing and is equal to r square plus omega L minus 1 over omega c whole square. Therefore, taking r square on left hand side, so 4r square minus r square is equal to 3r square, and the right hand side is as it is. Now also taking square root on both the sides, therefore under root 3r is equal to omega L minus 1 over omega c. But our task is to find out the value of capacitance, and so it is necessary that we should make C as an object. Therefore, 1 over omega c is equal to omega L minus under root 3r, and therefore omega c is equal to 1 over omega L minus under root 3r. Therefore, the value of capacitance C is equal to 1 over omega into 1 over omega L minus under root 3 of r, which is equal to, substituting the values of omega L and r. So 1 upon 100 into the value of omega is 100 again. Now the value of L is 5 Henry minus under root 3 into the value of resistance R, that is 100 ohm, which is equal to 1 over 100 into 1 divided by 500 minus, if you simplify this, root 3 is 1.732. So it is 173.2 because 100 was in the multiplication. Now I can write down this 1 over 100 as 1 upon 10 square into this value will comes around 326.8, which is equal to 10 to power of minus 2 divided by 326.8. Now 1 divided by 326.8 is 306 into 10 to power minus 5. It is only the value of 326.2, but here 10 to power minus 2 is also in the multiplication, and so the value of capacitance C is equal to 306 into 10 to power minus 7 Faraday. But it is better that we should write in terms of 10 to power minus 6 Faraday. So 30.6 into 10 to power minus 6 Faraday. And we know that 10 to power minus 6 Faraday is equal to 1 microfaraday, and hence the value of capacitance of a given capacitor in LCR circuit is 30.6 microfaraday, and hence illustration number 14 is over. Illustration number 15, in an ideal step-up transformer, the input voltage is 110 volt and the value of current flowing in the secondary is 10 ampere. So IS is given. It is 10 ampere. Also, The transformation ratio is given about 10. So R actually is given, it is 10, and that is equal to Ns over Np. So we know the another relation between the induced EMF and number of turns in the coil, that is epsilon S over epsilon P is equal to Ns over Np, that is equal to 10, and the EMF or the voltage is given 110 in the primary coil, and that implies the value of epsilon S can be obtained with this equation. Because epsilon P is having the value 110 and Ns over Np is 10. So epsilon S is equal to 1100 volt. And we know another relation, that epsilon PIP, because instantaneous input power and instantaneous output powers are equal, and so we can find out the current in the primary coil, because in the primary coil the current is unknown, but the current in secondary coil is known, that is 10 ampere. Therefore, IT is equal to epsilon S over epsilon P into IS. Epsilon S over epsilon P, that is ratio, means 10, and the value of current in the secondary coil is also 10. So current in the primary coil is about 100 ampere. And now for input power is equal to output power. So this is actually input power is equal to epsilon S IS. The value of epsilon S is 1100 into the value of IS is equal to 10. And so multiplying this quantity is equal to 11,000 watt, because it is the input power, and hence all three quantities are defined. And with this, the enumeration number 15 is also over.